All right, let's turn our attention now to section 9.6. It's about the root and ratio tests. Let's start off with the root test. The root test is a very powerful technique that allows you to evaluate the roots of the nth term of a series. Notice this is not the full series, just the nth term. If the nth term, as you take the limit as n approaches infinity, has an nth root that's less than 1, then the whole series will converge. So take your nth term, take its absolute value, and then take the nth root. So the first root of the first one, the square root of the second one, the third root of the third one, fourth root of the fourth one, fifth root of the fifth one, and so on. If n approaches infinity, that limit gives you a value less than 1, then the whole thing converges absolutely. Okay? If, however, you have that limit give you something greater than 1, or if it goes to infinity, then your series will diverge. The only inconclusive result is if the root test gives you a result, gives you a limit that's equal to 1. This is very powerful because it doesn't require you to compare this to anything else. It doesn't require any outside computation. The nth term of the series itself is all you need to know whether or not it converges or diverges. This gives you very conclusive results for both convergence and divergence. And the only limitation, which unfortunately will show up from time to time, is there are going to be some cases where if your limit is 1, then your test fails, right? Meaning you don't learn anything. So you'd have to go find a different test. Now, when you use the root test, there will be a particular limit that shows up from time to time. The limit as n approaches infinity of the nth root of n. We're going to go ahead and recall this because this is something that we do see in previous sections. Right? We use the properties of logarithms in previous sections to help us evaluate derivatives and to evaluate limits. Remember logarithmic differentiation? We can use the same kind of property of limits to help us evaluate this. So let's say here's the limit we're trying to find. Okay, nth root of n, that's the same as n to the 1 over n. Let's call that limit y. Take the natural log of both sides. Well, then the natural log of y is the limit of the natural log of n to the 1 over n. Okay, but now we have a property of logarithms, which is useful here. If you have a power inside, you can bring that outside as a factor. So here, instead of a power of 1 over n inside, we're going to have 1 over n being multiplied times the natural log of n. That's not calculus. That comes entirely as a property of the logarithm. There's no derivative or integral or anything there. It's just directly a property of the logarithm. Think back to chapter 5 was the last time we saw this. All right, well now dividing by a number is the same as multiplying by its reciprocal. So here, if I say times 1 over n, that's the same as dividing by n. Notice over here that's still natural log of y. I haven't changed anything over there since the first step. But now by L'Hopital's rule, note if this approaches infinity, that's infinite, and so is that. So this is an indeterminate form, infinity over infinity, which allows us to use L'Hopital's rule. The derivative of the natural log of n would be 1 over n. Well, actually, that's not quite true. Here, L'Hopital's rule doesn't work for continuous functions. What does work is that if you consider the continuous case. So technically, this right here is an incorrect statement to say I've used L'Hopital's rule. Here, L'Hopital's on the limit as x approaches infinity of the natural log of x over x has that equal to the limit as x approaches infinity of 1 over x over 1. The derivative of the natural log of x is 1 over x. The derivative of x is 1 if you're doing everything with respect to x. But what I'm using here is the fact that, these are just the discrete cases of this continuous function. So if this limit is equal to that limit, well then the discrete limit here must equal to the discrete limit here. So technically, the statement that from here to here is L'Hopital's rule is incorrect. From here to here is L'Hopital's rule. But this is just the discrete case of this continuous function. So I kind of took a little shortcut there, but since I'm the professor, I'm not supposed to do that, right? I'm supposed to show you every step. Here was the step. We use L'Hopital's rule on the continuous version of these. But it does give us a nice result. 1 over x over 1, take the limit. Okay, so for the discrete case, 1 over n over 1, take the limit. Here, 1 over n divided by 1. Let me just write that as 1 over n. And now from Cal 1, we know that the limit as n approaches infinity of 1 over n is 0. So at the end of all of this, we get the natural log of y is equal to 0. I can now exponentiate both sides, treat both of these as powers with the base of e. So if natural log of y is equal to 0, then e to the natural log of y is equal to e to the 0. Since logarithms and exponential functions are both 1 to 1, all of these transformations here from y to natural log of y and from natural log of y to e to the natural log of y, all of that's valid. But now e to the natural log of y is just y, and anything to the 0 is equal to 1. Oh, but y was that limit. Okay, so then that limit equals to y must equal to 1. So here, the limit as n approaches infinity of the nth root of n is equal to 1. So here, that's going to be one of those things that you either have to prove every time or it shows up often enough, you might just want to remember this. I'm not even going to say that's a theorem, although I suppose I could, and here's the proof. But in reality, it's just, here's a limit that you may wish to remember. You may wish to remember, oh yeah, that's equal to 1. Because it'll show up often enough whenever you use the root test. It won't show up at every time, but it shows up often enough. So let's see a couple of examples of the root test. All right. Let's consider the following problem, and here the same question that we've had in the last few sections has been, does this series converge? So does this converge? And of course, it's not just a yes or no question. You also are supposed to show what test we used and what were the results of that test. Okay? So let's start off with a reasonably simple one. At least it's simple if we are allowed to use the root test. Let's take the sum as n goes from 1 to infinity of 1 over, let's say, n to the power n. Okay, well, looking at that, I've never seen anything quite like that, the nth power of n, at least not in a sum. We've seen n to the power n in other instances, but certainly not something like this. Here, if it wasn't for that nth power, I would probably have a much easier time. That's what tips you off that you want to use the root test. Anytime you have an nth power that you're trying to get rid of, if it wasn't for that nth power, I suspect things would be simpler. That's when we use the root test. All right, so the way the root test works is take the nth term. Forget about the sum. Just look at the nth term. 1 over n to the n, in our case. Take the absolute value. Okay. Notice here, these were positive anyway. So here, the absolute values don't make a difference. However, I'm going to go ahead and write them anyway, just because in some cases they do make a difference. But here, in this case, it wouldn't really matter. And now I'm going to take the nth root of that. Okay. Now I'm going to take the limit as n approaches infinity of this. Okay. Now here, I'm going to rewrite this slightly. Like I said, the absolute values, when I take the absolute values, this is positive anyway. So here, that's just the limit as n approaches infinity of the nth root of 1 over n to the n. In this case, the absolute values made no difference, so I could write it with or without them. In the cases where it does make a difference, you may need to modify from here to here so that we actually do have positive values. But in this case, it doesn't matter. All right, so now I'm going to take the nth root. Well, notice this is a fraction, and when I take the nth root of a fraction, I can do the same thing on the top as I do on the bottom. So I'm going to write this as the limit as n approaches infinity of the nth root of 1 over the nth root of n to the n. Now, of course, the nth root of 1 is always 1, right? The square root of 1 is 1. The cube root of 1 is 1. The fourth root of 1 is 1. It's always 1. Okay, so let me just write 1 up there. And now the nth root of the nth power of n will leave me just n, right? The nth root and the nth power are inverse operations. So I just get this original base. Oh, but I know that. As n approaches infinity, 1 over n approaches 0. Oh, but now I'm done. Because notice, let's see here. Notice that I have the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. I mean, it's 0. 0 is less than 1. So here, because that's less than 1, then we know conclusively that our series will converge. And not only do we know it converges absolutely. That means the sum, as n goes from 1 to infinity, of 1 over n to the n, converges absolutely by the root test. You notice that the root test is a little bit simpler than many of our other tests. It may not be quite as simple as the ratio test. Remember, the ratio test, all you have to do is look at what the value of r was, and in the case of r being less than 1 in absolute value, you had one case, and if it was greater than or equal to 1, then you had a different case. But, so that was simpler. But the geometric series test only worked for geometric series. This works generally. This works for any kind of series with any kind of terms, not just geometric terms. What that means is there's going to be kind of a way of organizing this. There's going to be kind of a hierarchy of, do you want to figure out if a series converges? Okay, which test should I use first? You'll notice this one works very, very simply. Now, of course, it doesn't always work. There are cases where it is inconclusive. Keep that in mind, and when we get to the end of the section, we'll go over how to organize that. That method of organization is not foolproof 100% of the time, but more often than not, it'll show you the shortest way to find a result. All right, let's try another one. Let's consider something that looks like this. Does this converge? And the series we want to take is the sum as n goes from 1 to infinity of e, the exponential, to the minus 3n, just like that. Okay. Again, if it wasn't for that power n, this would be a much simpler number. In fact, it would be a constant. It would be e to the minus 3. So that's what tips me off that I want to use the root test. So go ahead and try it. Pause the video and see if you can attempt the root test here. Once you've gotten an answer, go ahead and unpause the video and we'll go through it together. All right, so to perform the root test, we're going to take the limit as n approaches infinity of the nth root of the absolute value of e to the minus 3n. Note, again, the absolute values don't make any difference because, of course, this thing is positive anyway, right? So plug in any positive number n, negative 3 times n. If you take e to that power, it's going to be a positive. So here the absolute values don't make any difference. So I can write that as the limit as n approaches infinity of the nth root of e to the minus 3n without absolute values. Okay. But now, if I take the nth root of that, remember how that works out? That's going to give me the limit as n approaches infinity of, and here I'm going to show the extra step. You may be ahead of me already, but I'm the professor and I'm not allowed to skip steps. The nth root is the same as 1 over n as a power. All right, square root is the same as a 1/2 power. Cube root is a 1/3 power. But now, whenever you have something that's raised to a power and you raise that to another power, the two powers multiply together. So negative 3n times 1 over n, that's just negative 3. So this gives us the limit as n approaches infinity of e to the minus 3. But that's a constant. There's no n here at all. So we can go ahead and just write that the limit of a constant is that constant, which gives us just e to the minus 3. That is approximately, let's see, that is approximately, e to the negative 3 is approximately 0.05, give or take, which is definitely less than 1. So because we have something that's definitely less than 1, that means our series will converge. So that means that the sum as n goes from 1 to infinity of, I forgot where my series is. Oh, here it is. E to the minus 3n will converge absolutely as a result of the root test. Just like that. Okay? Now you might say, well, that's great. That root test seems to work really, really well. So are you saying I should just use this one most of the time? Well, you should use it whenever it's available, whenever it works out nicely. What do you mean works out nicely? When doesn't it work out nicely? Well, there are some things that aren't really defined in continuous cases. In particular, there are some things that you can't take the nth root of. Say, like what? Well, the most common one we'll see in this course and throughout the rest of the chapter is the factorial. So consider the example. Let's say I wanted to take the sum, and then say, let's just, does this converge? Let's take the sum as n goes from 1 to infinity of n factorial over n to the power n. Now in this case, you may be tempted to say, well, let me take the nth root so I can get rid of that. And that's true. If you take the nth root of n to the power n, you're just going to get n, which is a nice, simple expression to work with. But what's the nth root of n factorial? Yeah, I don't know either. The nth root of n factorial is not something I can really know how to define because, first of all, factorials aren't even defined for continuous cases. All right, I don't even know what that would mean. So what that means is, for us, is that our root test may not be sufficient. So that's going to necessitate us to use a different test. Fortunately, this one works in a very similar way to the root test. This is called the ratio test. So the ratio test states the following, and it's going to look very similar to the way the root test looked. Instead of taking the nth root of the nth term, what we're going to do is we're going to compare the nth root with the n plus first root. The nth term with the n plus first term. We're not going to take a root. Rather, we're going to compare the nth term with the term right after it by dividing them. Now, once we do that, we're going to take the limit as n approaches infinity. So just like the root test, the ratio test is the limit as n approaches infinity of a thing. Now, that thing's different from one instance to the other instance, but the results are the same. If this limit is less than 1, your series converges, just like it did for the root test. If this limit is greater than 1, your series diverges, just like the root test. If it's greater than 1 or if it goes to infinity. And finally, if the limit is equal to 1, that's the instance where your test is inconclusive. All right? That means we don't know if the series converged or diverged. It means we just have no idea. So we would have to try a different test to tell us what happens in that instance. All right? Incidentally, we're not going to prove either the root test or the ratio test in this section, but just as a quick sketch, the root test and the ratio test, you notice they look very similar. It's because they're the same test. The proof of the root test is its own independent proof. And it's a bit long. We're not going to worry about it right now. But the ratio test is a direct result of the root test. Basically, once you have the proof of this, you tweak it ever so slightly, and it gives you this. So the reason these look so similar is because they actually are the same test under a slightly different look. So let's take a look at some examples of how to do this. In fact, we already have one example here. That's this series here. Does it converge? Factorials are notoriously difficult to work with because they are discrete only. There is no nice continuous version of the factorial. Notice I said nice. There actually is a continuous version of the factorial. It's not nice. It's not something we want to deal with, and it's certainly not something we should deal with in a calculus class. It's a little more advanced than calculus. But here we don't have to look at this as a continuous case, right? So even though this isn't defined nicely for us, it doesn't need to be. Because notice what the ratio test does. It compares the nth term, which is this, with the n plus first term, meaning the term where n is replaced with n plus 1. But if I divide a factorial by another factorial, you end up with a nice simplification. So here, let's go ahead and use this. Let's go ahead and determine something about this series using the ratio test. All right, so I'm going to take the limit as n approaches infinity of, and the way this works is, and make sure you don't get these backwards, take the n plus first term divided by the nth term. Okay, so the n plus first term is, start with this, but instead of n's, you're going to have an n plus 1. So this would be n plus 1 factorial over n plus 1 to the power n plus 1. Okay, now we're going to divide that by the nth term, by the original nth term. So this would be n factorial over n to the power n. So that's your a sub n plus 1, and that's your a sub n. Now, of course, we can simplify this right here, because after all, we're dividing by something, which means we can multiply by its reciprocal. So this is the limit as n approaches infinity of n plus 1 factorial over n plus 1 to the power n plus 1 times n to the power n over n factorial. But now things can simplify out quite a bit. Let me write this as the limit as n approaches infinity. N plus 1 factorial. Remember how that works. Here, I'm going to just grab a sheet of scratch paper here. Remember how factorials work. 5 factorial is start from that number 5, and 5 times 4 times 3 times 2 times 1. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And if that happens to be variable, well, that works the same way. If I have n plus 1 factorial, well, that's going to be start with that number and then start counting down. If you subtract 1 from that, you get n. If you subtract 1 from that, you get n minus 1. If you subtract 1 from that, you get n minus 2. Dot, 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 all the way till you get down to 3, and then eventually 2, and eventually 1. Okay? But notice, if you just strip off that first one, this right here is n factorial, because it starts from n, and then you subtract 1, and another 1, and another 1, until you get down to 1. So this right here is n factorial, which means that n plus 1 factorial is equal to n plus 1 times n factorial. Oh, but that's what I have here, n plus 1 factorial, which I can write as n plus 1 times n factorial. And over here, I have an n factorial, and hey, look, those just divide away like that. We can do something similar here. If I take n plus 1 to the power n plus 1, notice I can write that as n plus 1 to the power n plus 1. I can write that as n plus 1 to the power n times n plus 1 to the power 1. I'm multiplying two things that have the same base, so I can add their powers. Oh, but n plus 1 to the power 1 is just n plus 1. So I can write this as n plus 1 times n plus 1 to the power n. Oh, but that's this denominator right here. N plus 1 to the n plus 1. N plus 1 to the n plus 1. Well, that can be replaced by n plus 1 times n plus 1 to the n. Oh, but look, now these divide away. Just like that. And here I have n to the power n. Okay, so let's simplify what we've got. We've got the limit as n approaches infinity of n to the power n over n plus 1 to the power n. Here, notice they both have, it's a quotient, and they both have the same power. So we could write this as the limit as n approaches infinity of n over n plus 1 to the power n. Notice as n approaches infinity, this is an indeterminate form. This would approach 1, and this would approach infinity. Think back to chapter, what would that have been? Chapter 5? It was very early in the semester. I'd say section 5.5 or 5.6. Anyway, L'Hopital's rule. L'Hopital's rule is used for indeterminate forms. This, you'll notice, we used earlier when we used the ratio test. When we use the root test. Whenever you use the root test or the ratio test, because you're taking a limit as n approaches infinity, you'll often find instances where you need to use L'Hopital's rule. If you don't use L'Hopital's rule, there are other techniques, but here this one is simple enough. Now you say, well, wait a minute, I can't use L'Hopital's rule because that's not 0 to the 0 or 0 over 0 or infinity over infinity. Well, right, but here this limit can still be taken as long as we utilize some properties of the logarithm. But didn't we do that before? Yeah, that's a pretty common result. We'll often need to use logarithms to give us our limits. All right, so let's go ahead and finish this off. Here we need to find the limit of this. So let's see what that limit looks like. Here I'm going to use L'Hopital's rule, and L'Hopital's rule works for the continuous case. So here I'm going to go ahead and consider the continuous case. And if I can show that the continuous case has a limit that approaches some number, then the discrete case would also have no choice but to approach that number. All right, so let's consider the limit as n approaches infinity. So let's say x approaches infinity of x over x plus 1 to the power x. Okay. All right, so you might try yourself out here. If you're feeling a little brave about it, go ahead and pause the video and try to remember what we did back in chapter 5. Use L'Hopital's rule in the appropriate way to find this limit. Once you've found the limit, go ahead and unpause and we'll go through it together. All right, so let's go through this. Assuming you did pause the video and go through it, yeah, that was slightly painful, wasn't it? So here we're going to take y equals that. Okay, so that's the limit as x approaches infinity of x over x plus 1 to the power x. Okay, let me take the natural log of both sides. So the natural log of y is equal to the limit as x approaches infinity of the natural log of x over x plus 1 to the power x. But I have a property of logarithms that allows me to take the power and bring it outside as a constant, as a factor. So let's write this as the natural log of y equals the limit as x approaches infinity of x natural log of x over x plus 1. Here, I'm going to rewrite this ever so slightly. After all, I'm multiplying by something. Well, let's see. As x approaches infinity, you notice this approaches 1. The natural log of 1 is 0. Okay, so this is approaching 0. This is approaching infinity. Infinity times 0 is an indeterminate form. Well, yeah, but it's not one of the indeterminate forms that we like. We like 0 over 0 or infinity over infinity, not 0 times infinity. Oh, that's fine. Let's go ahead, instead of multiplying by x, let's divide by its reciprocal. So this is going to now give us the natural log of y is equal to the limit as x approaches 0 of the natural log of x over x plus 1 divided by 1 over x. So now, as x approaches infinity, we already saw this is approaching 0, and 1 over x is also approaching 0. Oh, 0 over 0. I can use L'Hopital's rule. So now this gives me, and here's where the extra painful part comes in. Let's take the limit as x approaches infinity. Here we're going to use L'Hopital's rule. And we're going to go ahead and take the derivatives of the top and bottom. Whenever you take the derivative of the natural log of something, you get the derivative of that something divided by that something. Okay, so let's take the derivative of this thing. Well, I use the quotient rule. That's going to be the bottom times the derivative of the top, which is just 1, minus the top times the derivative of the bottom, which is also just 1, over the square of the bottom. Okay, but now, whenever we take the derivative of the natural log of something, we take the derivative of that something, which we just found, and then we divide it by that something. So we're about to divide this by x over x plus 1. Well, notice we're going to divide by a fraction. That's the same as multiplying by a reciprocal. So here, I really should divide this by x over x plus 1. But I'm going to go ahead and skip a step. I know, bad math instructor, I'm skipping a step. And here I'm going to, instead of dividing by that fraction, I'm going to multiply by its reciprocal. This is still du over u. I just wrote the dividing by u as times 1 over u. Okay? And now, L'Hopital's rule says I take the derivative of the top, and I need to take the derivative of the bottom. Okay, well, that one's not too bad. The derivative of 1 over x is negative 1 over x squared. Okay, so now let's clean that up. This is going to give us the natural log of y equals to the limit as x approaches infinity of, well, let's see here. This entire numerator is just x plus 1 minus x. So that's just going to give me 1. Okay, so that's 1 over x plus 1 squared. I'm going to write that as x plus 1 times x plus 1, because in just a moment something's going to cancel. Okay, so all that's left here is 1. And here I'm going to write that as the product of two things rather than as a square. Times x plus 1 over x. All over negative 1 over x squared. Well, now you notice a bunch of things go away. Here, this drops away with that one. Which gives us, I'm going to go ahead and move this up here now. This is now equal, so now we have the natural log of y is equal to, well, let's see, we're left with 1 over, if we multiply these together, that's 1 over x squared plus x. I'm just multiplying the x on the x plus 1. And I'm going to divide that by negative 1 over x squared. Well, yeah, but dividing by a fraction is the same as multiplying by the reciprocal. So up here, I'm going to divide by this. Okay, that's the same as multiplying by the reciprocal of this. And the reciprocal of negative 1 over x squared is negative x squared over 1. Oh, my apologies. I forgot to write the limit here, didn't I? So it's not natural log of y is equal to that stuff. That's not true. The natural log of y is equal to the limit of that stuff. So natural log of y is equal to the limit as x approaches infinity of that stuff. Okay, well then that means that the natural log of y is equal to the limit as x approaches infinity. 1 times negative x squared is negative x squared over x squared plus x. Oh, but now that's one I can do. All right. At this point, that's still infinity over infinity, but I could use L'Hopital's rule, the derivative of the top and bottom. I could use L'Hopital's rule a couple of times, or if I want to go back to Cal 1, I could just divide everything by x squared. Either way, that limit is negative 1. So I get the natural log of y is equal to negative 1. And finally, I can exponentiate on both sides, here and here. And now this will give me, that's just e to the natural log of y is just y, and that's e to the minus 1. Or in other words, 1 over e. And there we go. So the limit as x approaches infinity of x over x plus 1 to the power of x turns out to be 1 over e. Oh, but that's just the discrete case of this continuous case up here. So up here, this one is 1 over e. But if you take 1 and divide it by e, that's going to give you 0.37, give or take. So that's definitely less than 1. And since I have my limit of the nth plus first term divided by the nth term, because that limit is less than 1, then that means that my original series would converge because of the ratio test. So the sum as n goes from 1 to infinity of n factorial over n to the n converges by the ratio test. Just like that. Okay? Note that the root and ratio test have a huge advantage over many other tests, and that is that they are conclusive most of the time. Yes, there is a case where if this end result is equal to 1, then the test fails and you don't know whether or not your series converges. But that doesn't happen very often. The advantage of the root and the ratio test is that they are usually conclusive. The disadvantage is that you have to evaluate a limit, and in some cases, limits can be complicated. L'Hopital's rule is a thing. It certainly helps, but it's true. Some limits can be complicated. Let's take a look at one more of these, the ratio test. The limits don't have to be complicated. Don't mistake this as being the only way a problem can work. Sometimes the limits are not anywhere near this complicated to take. All right. So let's go ahead and look at another example here. And to not waste any paper, let me go ahead and put it back over here, right underneath the ratio test. So example, here you'll notice this one is nowhere near as complicated as the other one. And now you kind of see why I put that one on its own page, because that one was going to be quite a lot. So here, let's take this. So does this converge? And let's consider the sum as n goes from 1 to infinity. Now notice here, I take from 1 to infinity in most of my examples. The root and ratio test don't tell you that you need to start at 1. If I started at 5 to infinity or 100 to infinity, it won't make a difference. But here, at any rate, from n goes from 1 to infinity of, let's say, 2 to the power n over n to the power 2. Okay, and here we could do this a few different ways, but I'm going to do it by the ratio test. All right, so let's take the limit as n approaches infinity of a sub n plus 1 over a sub n in absolute value. All right, well, let's see what that's going to look like. That's going to be the limit as n approaches infinity of absolute value. The a sub n term is just the term we already have. So it's 2 to the n over n to the 2. The n plus first term is, well, instead of having these as n, they're n plus 1. So that's 2 to the power n plus 1 over n plus 1 squared, just like that. Notice all of these terms are positive, so the absolute values make no difference. All right. So here, in my next step, I'm going to write this without absolute values. So I could just write this as the limit as n approaches infinity of, and now without absolute values. Notice I'm dividing by a fraction. Well, the same as multiplying by the reciprocal. So that's 2 to the power n plus 1 over n plus 1 to the power 2 is equal to, times, and now I'm going to reciprocate to give me n to the power 2 over 2 to the power n. Here, these were already positive. These were all positive. So we can drop the absolute values. Okay. So now I can go ahead and take this and I can simplify. Notice 2 to the power n plus 1 can be written as the limit as n approaches infinity. This can be written as 2 times 2 to the power n. After all, if I have power n and power 1 with the same base, I can multiply these together and add the n with the 1. Okay, times n squared over n plus 1 squared, and here over 2 to the n. But now notice these divide. And now we're left with the limit as n approaches infinity of, well, all that's left is 2n squared. And on the bottom, I have n plus 1 squared, which, in fact, I'm going to go ahead and square it out because that way it'll look like a polynomial, and I'll know how to take a limit without any problem. Here, I can write this as n plus 1 times n plus 1, which is n squared plus 2n plus 1. And now we're back in Cal 1. Or, this could even be done with an algebraic technique. You have a horizontal asymptote here. The numerator and the denominator have the same power. So the horizontal asymptote is the quotient of the lead terms. 2 over 1 is 2. Here you could use L'Hopital's rule a couple of times, and you would get 2. Or if you're using the standard technique from Cal 1, divide the top by n squared, divide the bottom by n squared, and either way, you're going to get 2 right here. Oh, okay. But now we're done because we found our limit. And in fact, this limit is greater than 1. Remember, for the ratio test, you're looking to see if your limit is less than 1, greater than 1, or equal to 1. If it's equal to 1, well, then you got to go find another test. But if it's less than 1 or greater than 1, you have your answer. Here, your limit is greater than 1, which means that our series must diverge. So the sum as n goes from 1 to infinity of 2 to the power n over n to the power 2 will diverge by the ratio test. Just like that. And that brings us to the end of all of our tests. We've seen a few different tests throughout these last sections in Chapter 9. And I mentioned that I was going to talk to you guys about a hierarchy, a way of saying, okay, this is the one that I should try first, second, third, fourth, and so forth. This by no means is conclusive. This by no means will always give you the shortest one no matter what, but it does organize your thoughts a bit, and it does tend to make many of your problems as short as they can be. All right. So first of all, if the question is, I want to find whether or not a series converges or not, to find if a series converges, the first thing you want to try is see if it's a special series. Can I use a series specific test? For a special series. Special series. Those special series are the geometric series, the telescoping series, the P series, and the alternating series. So these are going to be special. You'll be able to tell what they are just by looking at them. The geometric series, the telescoping series, the P series, and the alternating series test, the alternating series. These are the first ones you should try because they're the obvious ones. They'll stand out. If you have a geometric series, it'll look like a geometric series. In which case, there's a simple test. Is R greater than 1 in absolute value, or is it less than 1 in absolute value? If it's a telescoping series, what are the terms that don't cancel? Add them together. All the rest, that's it. You're done. The P series, is P greater than 1 or less than 1 or equal to 1? That'll give you different results, right? If P is less than or equal to 1, then your series diverges. If it's greater than 1, it converges. And the alternating series, that's the one that has the conditions that I have to have my A sub n approach 0, and I have to have decreasing terms. So here, all of these will stand out because geometric series all look the same. All right? They all look like the sum of A r to the n, and so that should stand out. The P series, they all look like the sum as of 1 over n to the p. The telescoping series, they all look like the sum of something minus something else. And the alternating series will look like minus 1 to the power n times a to the n, or the sum of minus 1 to the n plus 1 a sub n. All right. So try these first because they're the obvious ones, and when they're obvious, then you don't have a lot of work to do. You know you're going to work with this series, and you know it's going to give you a conclusive answer. All right. Now, what if it's not one of these? Well, then the next thing we want to do is ask, does it look like one of these? When I say look like one of these, you say, well, how close should it be to one of these? It should look like one of these except for maybe plus or minus or times a constant. So the next thing you ask is, okay, if this works, great, you're done. If that doesn't work, the next thing we want to do is we want to ask, okay, does my series look like a special series? In other words, it's not one of these, but it's really close to one. And when we say looks like, we mean really, really close. Like it's identical to this except for a plus a number. Or it's identical to this except minus a number. I mean really close except for maybe a constant. Okay. If that's the case, then what you want to do is you want to try a comparison test. Compare it to the series that it looks like. If you are going to use a comparison test, the limit comparison test may be a little bit more complicated to do because you have to take a limit, but it tends to work slightly more often. The direct comparison test is simpler to do, but it works a little less often. There really isn't a reason why you want one over the other. Just, choose your favorite. Which one are you comfortable using? In some cases, you might use the wrong one, so you'd have to try the other one. Personally, I find that the limit comparison test tends to work a little more often, I think, but that might just be a confirmation bias because I consider it to be simpler to use. Anyway, so you have your comparison test. Now, what if you don't have a special series, and what if it really doesn't look like one of your special series? Then you want to use the root and rate. Actually, the next thing you want to do is you want to try the nth term test. The reason we want to try the nth term test next is because it's very easy to pull off. If it's one of these, great. It's gonna work. If it's very close to one of these, okay, awesome. A comparison test will get you there. But if it's none of those, we want to use the nth term test. And the reason for that is because, well, if it's not a special series, there's a small chance it's just going to completely diverge. Remember, this can only give you divergence. But it's also really, really easy because you don't have to worry about a series. You just take the limit of the nth term. And if that limit of the nth term is not 0, well, then you're done. The whole thing diverges. But if it is 0, well, then the test fails. So you have to move on. So here, the reason I put this one next is because it's easy and quick to do. If it works, you're done. And if not, well, then you'll try something else anyway. This only gives divergence. Okay. After that, if that doesn't work, and really that shouldn't take more than about a minute to do, you're taking the limit of the nth term, then you want to try the root or ratio test. The root and ratio test work out really, really well, but you've noticed that in several cases, they are a little complicated to use. The limits that you're taking can be rough. Now, if they're not rough, that's actually a really nice one. But the root and ratio tests are a little more complicated because we have to take a limit of a rather complicated looking kind of terms. So I'll put this one a little further down. Now, in the interest of disclosure here, I know that there's a good number of people who like to put this right here. They'll say, hey, if this is not one of my special series, I'm going to jump directly to the root and ratio test because I don't care if it's a little harder to do. If I get my answer, I get my answer, and I don't have to worry about trying these. So this is sort of a matter of taste. You can put it here because, in a way, this one is almost the same as these, and this one is quick and simple. But some people say, yeah, I don't care about it being quick and simple. I just want to be done as soon as possible. So some people will put this one here. So this is a matter of choice. You can either put this one there or there. And then the last thing is the integral test. The integral test is usually considered the last effort. If nothing else works, you want to try the integral test. You say, well, why is that the last one I want to try? Because to use the integral test, you need to know how to take an integral. And think back to chapter 8. Taking integrals can be very, very complicated, even more than any of this other stuff. So the integral test is often considered to be the last effort, meaning, oh, I tried other things. they didn't work. Okay, then this is my last try. This is my last chance. If this doesn't work, I'm not sure what's going to happen. Also keep in mind, this is not an exhaustive list. There are other convergence tests besides the ones you see here, but these are the ones that are the most common, and they are the nice introductory ones that you can access in a calculus course. Series and convergence of series is a topic that does go on beyond calculus, but here, this is what we have accessible to us right now. And do keep in mind that this right here, this is an opinion. It's my opinion. It's how this is how I usually organize my work, but everyone's a little different. Like I said, some people use the root and ratio test right here. My personal recommendation is you really do use these first. If it's a special case, you can be done with the special case very, very quickly if you recognize it. But then here, it's sort of a matter of taste. This is my opinion, but you should form your own. Maybe start with this, and then as you do some of your homework, especially toward the later sections, section 9, 6, 9, 5, you may find that this doesn't quite work well for you. You don't like the way this organization is set up, in which case you can modify it on your own. This is not set in stone. This is just a starting point for you guys to try. That being said, the integral test is really the last effort. Yes, that's an opinion, but I mean, really, this is the one that is just the hardest to use. So go ahead and try your homework and form your opinion and see what works for you. As far as an assignment for this section, 9.6, try 13 through 67. Let's see, what would that be? 60, 50, 54. Oh, that's a little much. Let's do every other odd. This is the required. Now, if you want the extra practice, of course, you can do all the odds or even all of them. But this is the required for the extra credit. Oh, I almost forgot. When you're talking about this list of things, what should you do? There is one exception to the root and ratio test. Here, if the series contains factorials, things like n factorial like this, you're going to use the ratio test. Other ones, they're not going to cut it. If you see an n factorial anywhere in the terms of the series, you're 99.9% of the time, the ratio test is the right thing to use. So if the series contains factorials, the ratio test is probably the right one to go. Okay, so if you see a factorial in your problem, this hierarchy doesn't apply at all. Factorial, ratio test is really the only one that you're likely to actually be able to use because you can't integrate factorials. The nth term test generally doesn't give you convergence anyway, and factorials are a little difficult to handle in the first place. It's not a special series. Factorials don't appear in the geometric series, the P series. They might appear in the telescoping, maybe. They might appear in an alternating series, again, maybe. But the ratio test is generally the best one to use there. Again, that's an opinion, but start with this and form your own through your experiences. All right, so that's it for the section. If anybody has any questions, please make sure you reach out to me, and I hope you all have a nice day.